Hi everyone, Statistics 6840, Chapter 1, Introduction. This chapter discusses multiple linear regression, estimation testing, and diagnosis on the regression model. So this chapter uses Georgia voting data in 2000 presidential election. So in 2000, George Bush beat Al Gore, but the margin was very small. So the counting of the votes was a hot issue. Okay, so we use our console to discuss and demonstrate the data. So we use the library Faraway. So this library includes a GA vote dataset. Okay, so see the GA vote, help of the GA vote. So this is the data for Georgia presidential election. We have 150 observations on 10 variables. So then we want to use the GA vote data. So just so you can type the head of GA vote, then you can see the first 6 lines of the GA vote data. This is the county level data. So each line represents one county in Georgia, and we have 10 variables. So equipment to count votes. So we have 5 equipments: lever, optical system by center count, and optical system by county, maybe precinct count, and also some paper or some other methods. And the economic status of the county and percentage of African American, the rural or urban, and also in the Atlanta city or not Atlanta city. And the votes for Gore, votes for Bush, and votes for other candidates. And this is total, so the summation of these 3. And this is ballots, so some of ballots were invalid, so the number of votes are slightly smaller. You can also type the data GA vote package Faraway. In this way, we don't really need to load the data, load the library, but we can directly load the data. But anyway, we have already loaded the Faraway library, so it should be fine. Okay, so another way to see the data set is structure GA vote. So now you can see, for example, equipment have 5 levels and economic status have 3 levels and so on. Some factor variables and some numeric variables. And to see a quick summary of the data, you can type summary of GA vote. Then you can see this. For categorical variables, we can see the table, how many observations are categorized in this. So equipments, we have 74 observations of lever and 44 optical system with center count and so on. For numeric variables, summary function gives us some summary statistics, the minimum, maximum, and the first quartile. That means the 25% of observations are below this number. And median, 50%. Third quartile, 75%. Mean is the sample mean. Yeah, so this is the summary. You can see some counties are really large. At maximum, we have 263,000 votes, and small county only 832. And you can see mean is much larger than median. So that means a few counties are really large, but most counties are small. So data is skewed to the right. So now we think about the undercount. Undercount is basically the difference between ballots and the votes. but we want to normalize it, so we divide that difference by ballots. And since that we have data inside the data frame GA vote, we have to either attach the GA vote, or every time you have to put the $sign. So here, just the $sign, the attach is a little bit confusing function because often we forget which data frame we attached. So we just name this as G, and every time we type G $sign, then we define G undercount as G ballots minus G votes, and we divide this by G ballots. So basically for each line, we calculate this. So the resulting, the undercount, this G $sign undercount is again a vector of 159 observations. So the same size, the sample size. Okay, so now if you type the summary of G, maybe just we want to see the summary of this resulting vector, you can see this. So on average, the Georgia has undercount of 4.379%, at maximum 18.8%. This is very large. Minimum actually 0. Yeah, so this can be done by another way. So if you don't want to type the G $sign every time, and you don't like to attach data frame either, then you can use the with function with G sum ballots. Sorry, that's ballots minus votes, then divided by ballots. Then you can see 159. If you name it, just you can use this in the place of this. So we have several ways to do that. If you want to get just the overall percentage of undercounts, you can take summation for each of the denominator and the numerator. So you can get 3.5% is the average. Okay. So this is the overall undercount over overall ballots. So it's different from the previous, the sample mean undercount rate for counties. Okay, so that is we calculate the undercount percentage for each county, and after that we take the average. So the numbers are different. Okay, so now we want to get a histogram of this undercount. We have seen that the one county have 18.8% of undercount. So just we want to check if that is extreme or just distribution is almost the normal. So you can make a histogram, G undercount. So this makes histogram. You can see, yeah, table somewhere. So this is the histogram. Okay, so sometimes, okay, so we have the very large observations, but sometimes we want to fit some smooth curve. So this histogram isn't that bad, but if histogram is not really smooth, we want to see some tendency. So in such a case, that we want to have so-called density estimation on the histogram. And that can be done by plot density. So density of G $sign undercount. So this makes the density information, so smoothed curve. Then we have this density curve, it's smoothed. And actually, this was made by overlaying the bell curve. So if we combine several bell curves, then basically this is kind of the summation of that, then it becomes normal. It becomes smooth, sorry. It becomes smooth. We overlay many normal distribution with different centers. Sometimes we want to put these side by side. In such a case, that you can change the parameter of graphics. Parameter MF row, the multiple figures by row, 1, 2. So that means we have one row but two columns. So the two graphs, the side by side. Then histogram and the plot. Then you can see the two graphs in one window. And you can then compare this. And sometimes you further overlay these two graphs. But to do that, we need several things to do. At first, this is frequency, and this is density. The frequency is just the counts. But the density makes this area under the curve equal to 1, because basically the proportion matters. So if the total area is 1, it's easier to interpret. Area corresponds to proportion. For example, the area below 0.05 means the proportion below 0.05. Okay. So we have to use the density scale for both ones. So we have to change it. And also remember that if we overlay two graphs, that we have to set everything. So x range for x and range for y exactly the same for two graphs, and also these labels and titles. So everything should be the same. So we have to do several things. So okay, so if we want to overlay, we put only one graph in one window. So we go back to MF row 1, 1. So this is the default value. So just one figure in a window. And then, okay, so histogram we put, but we have to get the density histogram. So frequency is false. We need this option. And okay, so this histogram ranges from 0 to 0.2. So for histograms, we have to specify breakpoints if we want to change the X scale. So breakpoints are 0 to 0.2 by 0.02. Okay, so we have 10 bins between 0 and 0.2. 0 to 0.02, 0.04. So increment is 0.02, and we have 10 bins. So in this way. And when we make a density histogram, that you can expect that ends around 20, right? So we set y limit as 0 to 20. Yeah, so we put this breaks sequence. Then we get this. Then to overlay, we have to set parameter new is equal to true. Then after that, we plot density, but we have to use the same X scale and the same Y scale. So X limit is from 0 to 0.2, and Y limit is from 0 to 20. Then you can overlay these two. And still, we have some, we overlaid the different X labels. So we have to adjust this and also main title, but you can just adjust it. Okay, so this is how to create the figures and how to create histograms and the density histograms. And just in case, at last, we put the parameter new is equal to false, just to prepare for a new graph.